Hello everybody, in this tutorial we explore the performance difference between the implementing a vectorized UDF, user-defined function, and using a built-in function. We will focus on calculating a moving average for a sample dataset and compare the execution time and physical execution plans. Okay, first of all, what is the vectorized user-defined function? In Databricks, a vectorized user-defined function (UDF) refers to user-defined functions that operates on entire columns of data at once rather than processing one row at a time. This is in contrast to traditional row-wise UDF, which operates on a single row of a data time. Vectorized UDF are designed to take advantage of the underlying distributing computing framework in Databricks and significantly improve the performance of the data processing task. The term vectorized is borrowed from the linear algebra, where operations are performed on entire vectors and matrices rather than individual elements. Similarly, in the context of the Databricks, vectorized UDF operates entire columns of data as a single unit, which can result in more efficient processing compared to row-wise UDF. Vectorized UDF are typically implemented using a programming language that support vectorized operations such as Apache Spark, built-in functions, or libraries like Apache Arrow. This UDF can be written in language such as Python, Scala, or SQL, depending on the Databricks environment and the specific use cases. The benefits of using vectorized UDFs include performance improvement. Vectorized UDF can take advantage of optimizations in the underlying process engine, leading to improved performance compared to row-wise UDF. Parallel executions. The vectorized approach allowed for parallel execution of the operation on different partition of the data, leveraging the distributed nature of the Databricks. And finally, code simplicity. The vectorized UDF often result in simpler and more concise code as they abstract away the need for explicit looping over rules. Okay, keep in mind that exact implementations, details, and syntax for vectorized UDF may vary depends on the version of Databricks and the programming language used. Always refer to official documentation for the specific version you are working with for accurate, up-to-date information. Okay, here we go. First of all, importing essential pyspark components and libraries for data processing. From pyspark.sql import spark session. Okay, and from pyspark.sql import functions, import column average, and finally pandas UDF, and from pyspark.sql types import double type import time from datetime, import datetime time delta, and import random, and finally from pyspark dot SQL dot window import window. Okay. Okay, next step, create a Spark session. Spark equal Spark session dot builder dot app name vectorized UDF comparison dot get or create. Okay, generate random sample data for the value column. We have a data set with two columns, date and value. Random values equal random dot uniform, okay, and 1 and 50 for underscore in range 90. Okay, and this line of code generates a list of the 90 random values that could be used as a sample data for the value column in the data frame. Each value in the list represents a random measurement or observation, and the values are uniformly distributed within a specified range. Okay, next step is generate date values for the date columns. Start date, okay, start date, date time dot str strip time, okay, and here 22, okay, and D and M. Date values equal start date plus time delta dot days, okay, equal I dot str time okay year for I in range 90. Okay, this code represents a list of the 90 days values starting for 2024 0101 and incrementing by 1 day for each subsequent date in the list. The date values are formatted as a string in the YYYMMDD. Okay, and create next step is to create a sample data with a random values. Data equal list zip date values and random values. Okay, and define the schema equal date and value. Okay, and create next step is to create a data frame. df equal df dot pyspark dot create data frame data and assign the schema equal schema. And convert the data column to a timestamp type. df dot read column. Okay, column name date and drive from date column date and cast to timestamp. Oh, sorry. Data from object has no okay. Okay, and next step, define the vectorized UDF for calculating the moving average. Add sign pandas UDF. Okay, and double type and def moving average UDF. Okay, value PD dot series and here PD dot series. Okay, and return value that rolling window equal to and minimum periods yields example 1 and call min function here. Okay, this is a decorator. Okay, this sorry, this is apply the function immediately following it. In this case, it's used to define a pandas UDF and data type. Okay, the all data type is specifying return types of a UDF, return type of the UDF, indicating that the UDF will return a pandas series with the element of type double. Okay, and here here. Okay, this line defines a Python function named moving average UDF that takes a pandas series value as an input and returns another pandas series. The function is annotated to indicate that it returns a pandas series PD series. Okay, and finally okay, and here okay, and here inside inside the function, this line calculates the moving average using the pandas rolling window functionality, and this part creates a rolling view of the input pandas series with a window size of 2 and minimum of 1 period. Okay, and final mean. This calculates the mean of each rolling window. Okay, and okay, and finally time of the execution of the vectorized UDF. Start time UDF, okay, equal time dot time, and here result df UDF, okay, and equal df dot with column moving average UDF and moving average UDF, okay, and call and value, and here and time okay, and time UDF. Oh, sorry, time dot time. Okay, okay, and next step is time the execution of the built-in function. Start time built-in time dot no. Oh, sorry. Okay, and window spec equal window dot order by date, okay, and rows between -1 and 0 result df underline built-in. Okay, df that with column rolling average built-in and average column value. Okay, get over spec window spec, and finally end time built-in equal time dot time. Okay, this code calculating a rolling average for data frame column name value based on the ordering of the date column. It's used the window specification that include the current and immediately preceding row. And the result is stored in a new column, rolling average built-in. Okay, and show the result UDF that show. Okay, and here built-in end time built-in minus okay, and finally yes. Okay. Okay, you can see difference between two columns. Sorry, two functions. Okay, and here plain Okay. And compared to execution plan, the plan UDF, the physical plan you provide suggests two different execution plan for calculating a moving average. One using the Python UDF arrow eval Python, and other using the built-in Sparks function window with the average function. Let's analyze each plan and discuss potential performance bottleneck. Pros: utilize a Python UDF arrow eval Python here. Python here, allowing for flexibility in defining custom logic. Cons: involve the Python executions, which may be slower compared to native Spark functions due Python's global interpreter like GIL, limited optimization for distributed processing. Okay, and plan 2, window function, and here use the built-in Spark window function, designing for distributed processing, leveraging Spark optimizations and parallelizations for improved performance. Cons: may like the flexibility of custom Python UDF for complex operations. Overall analysis is the pyspark window function approach is likely to more performance due to Spark optimizations and parallelizations capabilities. The Python UDF approach might be useful custom complex logic, but may be slower due Python limitations in distributed computing. Thank you very much for your watching.